Well, hey, welcome everybody to the P2 Live Forum today, December 2nd. Today we're in Parallax. I'm going to kick this off from here, and then I have to get back to work, so I'll pass this over to Chip in a bit. But since we're here, I thought I'd show you a few things if you're interested. You guys want to see anything
Chip
interesting?
know how to run the
Absolutely
computer?
not interested.
It's totally boring stuff. So
Yawn.
I'll show you the P2 Edge breadboard and the process for putting them together. So at the moment we're stuffing them, and we are very short-staffed at Parallax, and our shipping is closed, and we're missing some people, and basically you guys are buying everything we're making, which is good, but we just can't ship it. So I'm helping today, and we also got David who came in to rescue Terrell. So the process of stuffing a board takes about 8 minutes if you're moving fast, and the parts all fit really nicely. We have to make sure that they are sitting perfectly upright before they go into the solder machine. So the process would be that we pick up a board, and then we set it here on the tray, and then we make sure all the parts are sitting straight up and down. And it's difficult because some of them are a little bit loose, but the ones that press in tight we don't have to worry about. And we want everything flush against the circuit board, and we do a final check for any polarity, you know, like the caps and the LEDs, and that the reset button is in the right place, and that the prop plug header is the right amount, not tilted forward. And then the selective solder machine, which is this machine, which is one of our favorite machines here, takes over. And the way this tool works is the programming. Some of you may recognize the interface for it. Let me see if I can give you a better view of it. So this is actually a Mach 3 software, like you use on CNC machines. It was customized for the ACE selective solder by the company that makes these, which is in Spokane. So it's an American machine. And the way Terrell programs it is he drags this solder around to the right spot, and then he identifies how long it stays there, how fast the solder flows, what the dwell time is, and that writes the G code that you're looking at. Is that how it works? And then, so it writes the G code. You guys hear all that?
I do.
Okay, yeah, he's talking about how it could step and repeat, and there's some ways to automate it.
Is that machine running Windows XP?
Is that Windows XP? Yeah, it is running, and it's running Windows XP. No internet connectivity, so.
Yeah, I was going to say, I hope not.
So these are going through. They take about 2 minutes to run. Then David's going to help us get up to speed on this. Stuffing boards, further running Terrell's program. But our backlog, as I mentioned, we're very short staff. Like the P2 edges are sitting over here, awaiting some love. So what will happen to these next is we will, I think the way this is designed is they snap apart, and we probably run the pizza cutter, which is this tool. It's an ominous looking machine, isn't it?
Geez, yeah.
Yeah, and what's scary is how quiet it is too. But as you can see, it's had a lot of use. So once you line up the boards the right way, like, I don't know if you guys can see this. So
You almost sounded happy when you said how quiet it is.
Yeah, it's not on right now. So you line it up just like that, and then you feed them through, and then it depanelizes them. Then you can step it over and get the other tab off, and then we sand them.
Where's the safety guard?
You got to get close to the work. Yeah, so these are waiting, and then we have like...
There's a guard around those wheels. You can see it.
Yeah, you can't...
Only the board can slip in. Ken, why don't you turn it on so we can hear it?
Okay. Start and stop. Why is it quiet? I don't know if it's actually powered. Let's see here, yeah? Let me get Terrell. Oh, here it is.
The boss needs to get help.
Yeah. Well, only because he's not paying attention to me right now, I could do this. Okay, so now it's on, and you can't even hear it. We
That
could
is
send one
fun.
through if you want to see.
Yeah, let's see.
Okay.
And so you have to have the board scored anyway. So it feeds it on a really tight path.
So there's a little bit of resistance there. This might have to be raised. Okay, I don't think it actually, this might be,
Would you just score
Yeah.
up the connector?
Notice how slow it's turning. It doesn't really need guards with how slow it's going.
I think this might need to be adjusted, but I'm not really sure because it's a tight fit. So I'm going to let the guys do it, and maybe I'll come back to that.
If it goes faster, it'd make heat, wouldn't it, on the board?
Usually we do speed it up, so I think that speed is really
Yeah.
slow. It was on 1.
It doesn't, it's like scissors that don't touch. It just kind of squeezes and cuts its way through without burnishing anything. There's no drag on the tool against the work. It just goes through at the same speed as the cutter.
And here's the stenciler. So this is where we start the SMT work. And then it goes into the pick and place, which y'all have seen. This should be running today, but again, we're a little short. Then to the oven.
Is
Over
it a
here.
profile oven?
Yeah, it is. Chip knows more about this machine. Makes
I had to
cookies.
run
What,
a
the oven?
Yeah, I ran a profile oven when I was making thick film circuits.
And here we're actually washing some Johnny Macs, making sure he's squeaky clean.
Yeah, I like how it's a dishwasher, basically. Fancy dishwasher.
The most complicated
Yeah.
thing we've sent through that pizza cutter were these boards.
Oh, that's a long time ago.
Yeah, and
Yeah.
these would get sideways sometimes if you weren't careful, and it'd cut the board in half. It was a little bit scary.
Yeah,
18,000 of them.
pizza cutter is a good name for it because it's literally one-to-one movement. Like the roller is going across the board. It's not like a saw where it's spinning against the board.
Hey, David,
It's like rolling and pinching.
can you do a pizza
Yeah,
cutter
it's
demo?
like scissors.
We'll see if David can show us that. Everyone seems to like this.
Ken,
Yeah.
if walking robots, are getting so popular now, do you ever think of bringing out something like the stamp bug again?
I would like to. There's so much we want to do. We need to restart our. I kind of got that stuck, David. So we'll come back to him in a minute.
Tell David the guard needs to come up.
Yeah, it looks like the little guide needs to raise.
Hey, Ken, show those big cylinders that are used for the deionized water.
The big cylinders for the DI water.
Where are they? Oh, or do we have it? Oh, that thing there, yeah. That's some kind of like ion trap or something, and the water that comes out is deionized. So that means there's no residue on the board when it dries.
So you don't have to clean your boards with trichlor like we did in the
No.
old days.
They come out.
I love, the old ways were actually excellent ways. See that big oven there? We had to buy that. This was like a European Union directive that we get rid of tin lead solder and we go to these higher temp solders. So Heller, this German company, these ovens are all over the world. I think they must have sold, 100,000 of them. And they're required for the high temp profiles. And then the trouble is the solders don't wet as well as they used to. They don't clean as well as they used to. I really like the old ways.
And
Still have
also
lots of lead
Give you a
solder left.
closer audio.
you run into problems with
There you go.
sensitive components to heat, like the RGB LEDs can't take the heat that's required for some of those.
Right.
Thanks, David. Carol, to answer your question, we would like to do some of those products again. We just have to get back on our horse, so to speak,
Mm-hmm.
because we've kind of fallen behind. I mean, we can't do everything at once. The P2 took a lot of energy, and we want to be running these, making more motor mount and wheel kits, which we will momentarily. At the moment, we're making, let's see here. I could show you.
Motor mount and wheel kit, is that for dirt track robot?
That's
Like
the 12 volt
dirt track.
aluminum 6-inch wheels with the special motors.
Yeah, the
The
big
window
Arlo
motors.
ones.
Yeah, the Arlo thing.
Oh, the
Thanks, Roy.
Arlos. Okay.
So we're building the gripper parts right now, another 100-unit run.
Oh, that's one of the things I'm working on. You remember I bought another Arlo, and I'm going to mount this on top of it. Ugh! A big arm.
All right, lovely.
Yep, big metal arm. Out of China, of course.
Oh, these are actually the gears too, the main gear. We could not have designed a more expensive product to make. But
Then what? The
then the
P2?
gripper. No,
Oh,
the gripper makes me forget about the P2. But before you guys carry on with your fun, I'm almost done. So the shipping area, as I mentioned, we're very much behind. Chip, you'll be interested in this. All these components have not been received. There's orders to ship. Shipping staff is out. And
box is mine.
yeah, here's Carol Hazlitt, Roy Eltham.
Yeah.
We're going to need a bigger box.
Exactly.
I already got my order, so that can't have been mine.
So there
Well,
are
I
a
think
couple.
Roy and I were both typing at the time you were talking on the very first day you introduced it.
Are you guys in
We
Santa
got
Clara
'em.
County where you're at there?
No, we're in Placer County,
Oh, okay.
Rockland.
Santa Clara is like locked down hard right now. They shut down everything.
Yeah, I took a friend out to lunch today in Placer County, and it felt very similar, although they still have outdoor dining.
Well, I know they moved the 49er game to Phoenix because they can't even have a game there.
So there are three items,
Go ahead.
okay, that I picked up on this week that were of interest to people. First one is Greg's question, I believe. No, I think Greg was asking about SPI. So question came up. One thing that would help is to go over the meaning of the symbols in the SPIN2 documents, specifically the ASM instructions. Not sure what they do, but how to read what has been answered there. I'm not sure I understand that. A lot of it I understand, but the bit fields are a little confusing. And then I wanted also Tubular to show off the temperature sensor with mu. And John has agreed to share also some SPIN1 to SPIN2 code considerations with Chip's help. So those are three things that you can go over in any particular order desired. I'm not sure what would be of most interest to people. Maybe if Tubular's here, we can knock out the Python bit first.
All right. So I cleverly posted a sort of a how-to of how to connect up a LM335 temperature sensor to the P2, and I posted it in probably the harder place to find it, in the general discussion area. I thought, I'll get around to fixing that up or asking the moderators to move it later. And then Ken posts a link to that discussion, which kind of locks it in place now. But that's fine. So just over on the forums, in general discussion, you'll find there's a post showing a sort of a single page picture story showing some Python code to exercise a LM335Z temperature sensor, which have been around for a long, long time, decades. They're kind of the kind of part you can get at almost any electronics shop. They're not super accurate, but when you've got a sort of an industrial problem which just demands some investigation or some, anything on hand will do, and just give you some idea of relative temperature, even if it's not absolutely accurate. So I'm just going to post LM335 temperature sensor hooked up to the P2. It just requires two wires. One of the grey wire is connected to ground, and the red wire is connected, in this case, to P16. So these temperature sensors, there's an optional trim pot, like a calibration trim pot, if you're fussy about absolute temperature. You can use a 10K trim pot to to maybe do an ice bucket calibration for zero temperature. But the nice thing about hooking this up to the P2 is literally you can get away with just the 2 wires to the sensor, and you can use the 1 milliamp pull-up current source, which is built into every single P2 pin to bias the temperature sensor. And what will happen is the temperature sensor puts out 10 millivolts for every Kelvin, every degree Kelvin above absolute zero, which means that at room temperature, it's putting out something around 2.98 volts. And so we're reading that into the P2 using the analog to digital conversion in its fairly basic mode, which I'll show you here in Mu. That's not going to work. Oh, yeah, there we go.
So Lachlan, at 3.3 volts, how many degrees C is that?
I haven't run the calculation, but it's going to be 300 millivolts divided by 10. It's probably about 30 or 40 degrees above room temperature.
In Celsius?
In Celsius, yep. So maybe, 60 or 70 Fahrenheit above room temperature?
You said it's 10 millivolts per degree C?
Correct, yep.
So, yeah, so 330, and there's 273 Kelvin is 0 C, right?
Yep.
So it'll go to 57 C at 3.3 volts. But then you're kind of running out of the current source by then.
Yeah, so next week I'll post, maybe next week or sometime soon, I've also used the LM334Z, and the really nice thing about that is you can kind of choose your scaling. And that means you can stick room temperature at, say, 1.65 volts and zoom in on the signal.
Yeah.
So that's only one, that just adds one component more, makes it more complicated, but you know, we just end up with one extra component, and that lets you sort of use the zoom range on the P2, which is good. Maybe if I do a screen share just for a moment and go through the Python code, and then you'll see I've got a sparkler here. We haven't actually run any tests on this yet, and we've got a flame there to illuminate the sparkler, and then we'll see if we can do a sort of a live temperature view of the sparkler temperature as it runs past the sensor.
Well,
so back to
the sparkler will throw off some slag and make a mess around the board, won't it?
yeah. So we've got a like a ceramic dish kind of thing, which we'll use to capture everything, and you'll see both the temperature sensor and the code here in Mu. So in Mu, you have 3 windows, which makes it kind of convenient for things like this. You've got the code window up the top left, which has got the Python code, and what you see on the screen is pretty much, well, it is the entire program, so there's about 20 lines of code. Down in the bottom left, you've got like a terminal window, which shows what you see coming out of the serial REPL in MicroPython. And in the right-hand side, you have a plotting function which displays like 100 data points. Just to run through the code briefly, all we're doing, we're initializing pin 16 with a 1 milliamp high current source. So that's a pull up to positive, a current source injecting 1 milliamp down through the sensor. We're turning on the analog to digital converter in 1 times mode, which means it's got the full 0 to 3.3 volt span, which we need to look at the 3 volt signal. And in order to get a value out, we just count the number of highs within a period of time, and that period of time is 1 million ticks. Okay, so that gives us quite a sort of a large count, but it also gives us a reasonable sampling rate of around 250 samples per second. And the final trick is just to put the switch the A to D converter on in addition to the digital current source, which is driving the bias, which are those TT bits at the end. In between samples, we just delay for 0.3 of a second, and because we're taking about 100 points, that means, you know, that the experiment runs over a 30 second duration. So when we click run on this graph is going to zoom in on. Sorry, we probably need to do a dry calibration run, and what that'll do is just put a 0 value in for the entire duration of the test, and sort of clear out the other values, and so it'll start sort of zooming correctly. And then we'll start a new run, which will kind of auto zoom to that run. So this is our sort of zero run, which will just put zeros all the way through. We've got MicroPython also outputting the values to VGA at the same time as it's working with the PC. So there's a sort of a zero run. Now we'll click go again, and this time we'll actually, I'll put my fingers onto the sensor. Okay, and we'll ramp the sensor temperature up, which I'm doing there. And then we'll put some freeze spray on it to ramp the temperature down. This stuff is pretty brutal, so I only give it like a really short burst. And you can see that the temperature's gone down again. And then we'll heat it up again with the fingers. Maybe even actually put a flame under there, see if it'll speed it along. Okay, so there you go. That's while that's not really calibrated to degrees Celsius, the graph is just in a sort of a ADC count value. So it's going between -8,000 and +8,000 out of those 1 million count samples. You can work out the kind of voltage range which that is, and we could add a couple of lines to convert the units in Python into degrees Celsius, which we'll get onto for next week. And the other thing we can easily do, because all this is contained in one smart pin, we can have more than one sensor. We've got another 10 sensors which should arrive today, and we'll just hook them all up so you can have like 8 values graphing at once, and that should make for a bit of a better demo. So Brian and I in our travels, we've both encountered industrial or applications where you want to take temperature readings across multiple locations. Here at work, we have a system which looks at 8 different temperature locations around a factory. And Brian's done work with engines where you need an array of temperature sensors. And so the fact that you can have one of these on every P2 pin, you can have up to 60 or so of these sensors if you really wanted to, without too much trouble. You just have to switch these things on, and it's all contained in the pin, and all you've got to do is go around and read the values. All right, so we got any questions to that point about the code or the basic operation?
Hey, well, Lachlan.
Yeah.
I have a question. So how would someone do this? I mean, you're using here this is the Moo editor, right?
Yeah, that's the Mu editor. So this is one of Ken's favorites, which is got, the multiple windows in it, which makes it easy to view both the code and the results of what you're doing at the same time. It also runs cross-platform, so you can run it with Mac or Linux systems, possibly even other Android systems. I'm not entirely sure, but certainly runs on many platforms. A really good introduction, I guess, or simple program for just getting up and running. It does have some annoying features, like if you want to save a program as, it's a little bit different to what we used to, where we just have it like a save as kind of command. But by and large, as a starting point, it's useful just for getting up and running. Of course, we can take a bit of time, and we'll be able to get this into Spin with its debug windows as well. It won't take a lot to translate that code into Spin too, and have an equivalent, but of course that'll just run on the PC at this stage.
A lot of the schools are using Mu. I had to learn it to help my granddaughter with her homework. It's big in STEM.
Yeah, I think that's right. The guy who created Mu was very focused on keeping it straightforward to use, and had education in mind all the way through. And my belief is he came at it from a sort of a music education background, or possibly a philosophy background. He sort of knew that he needed something fairly focused. This is Nicholas Tulurvi, I think his name is, over in the UK. So, yeah, it's nice and sort of focused on keeping you focused on the application and running the experiment. But I'm sure we'll all outgrow it, but as a starting point, it's pretty good.
So if someone wanted to run this, they would go get you, install it on their system, and then what would they get from you? Or I'm not even sure, is your MicroPython like available for anybody to use at this point? It's not.
Yeah, we've uploaded, the MicroPython has been uploaded to the Parallax website. We have it on GitHub, so we're developing, and we put new versions on GitHub. But there's on the new Parallax website, there is a link on getting started with Python, and that will take you and point you to where to download this from GitHub. And so you don't really have to understand GitHub. You can just go to the Parallax site and go through that way. And on the Parallax site, there are instructions for how to flash MicroPython onto your board.
Gotcha, okay.
Yeah, so if this is up already, we will tidy it up a little bit and make it a little bit more clean, but But, you know, we welcome any feedback if people find that they're getting stranded somewhere, but it's pretty straightforward. The only thing we suggest is that you do actually install MicroPython into the Flash on the board. And that's just because MicroPython and when using Mu, it'll frequently reboot, like when we move between modes. And so by installing it in Flash, it sort of starts in under a second, and it's just a nice sort of user experience to do it that way. So.
Okay, so that's great. So someone can actually get this stuff and run the code that you're showing here, and then write their own MicroPython code.
Yeah, when we get a
Yes.
moment, we haven't had a moment, but we'll just create a video just walking through that process. Even though I don't think it's difficult, and there are instructions on the P2 website. It's just the kind of thing where, you know, just a video to show walking through, and then maybe taking some readings. You know, that's pretty straightforward to create. It's almost just the same as what we're doing here, but just with a bit more structure.
Right.
Tubular,
Yeah.
are they using it where you are on hardware to do things with? Because the schools up here, all
Yeah.
they have the kids do with it is graphics,
Right.
movable graphics, and that's the end of the class.
Yeah. Yep. No, you can. It has some game plugin, the Pygame plugins. It has a couple of different modes, but
they're not using hardware with it. Don't walk on
no.
the keyboard.
Yeah.
Go back.
Yeah. I think that's true. There's different parts of the curriculums where they're just trying to engage kids with through games. Eventually, we'll work out how to hook all that stuff in together. You know, they're just different parts, different modes of Mu. So Mu has about 4 or 5 different modes you can operate it in. We're using what's currently known as the SP mode, which is actually just a sort of a pure REPL. It just means sort of it's using the serial link in its kind of purest form. But there are special modes for Pygame and Web Flask development, I think. And these are all sort of within the Mu framework, and you'll be able to find things online. So there's a reasonable amount of content. You know, if you get used to Mu, you can span across quite a few different sort of experiments and things. Obviously, we're focusing on hooking up sort of low-level devices with the P2 and looking to build hardware around that. But you know, it's just a good, you know, Ken put us onto it, but it's a good starting point for being able to do things, and it translates well into education. I think people outside of education will probably regard it as kind of limited. It doesn't matter when you're just getting started, you know, when you just want to get that confidence that things are working and that you can replicate results. I think it's quite good.
Lachlan?
Yes.
You know, a silicon diode has a temperature coefficient in the forward direction of 2 millivolts per Celsius.
Yep.
Do you think the Propeller and the the current source and the A to D converter would be sensitive enough to use that? Because with that, they're very cheap. You know, an LM or a 1N 948 and a little forward bias current generates that voltage.
Yep, you are absolutely correct. And
Yeah,
well, we actually, before we were doing the temperature sensors, we were looking at LEDs and using the LEDs as a photo sensor, sort of biasing the LED with a small current and reading the result. And we had some success in that area. I sort of emailed those, a quick screenshot across to Parallax, and we'll come back and we'll probably do a similar kind of tutorial on running LEDs as photo sensors. Here on my desk, on the other side of the desk, these are just different LEDs which give you different responses. Just purchased from the electronics shop. I keep them in their bag just so I can remember which one works best. But
those in a current mode or in a voltage mode of some sort?
Yeah, effectively, well, you're using it, I guess it is a kind of a current mode because it's a photo sensor generates a current when light is incident on it. So you need like a bright white torch. But you can actually, you can get a response from the LED, even though it's being forward biased with like a 10 or 100 microamp current source. You can get a response back. And of course, you need to use like a red or an infrared kind of LED to capture the rest of the spectrum, for physics reasons, which I'm not sure if it's Stokes's theorem or other theorems, but basically they say that, you know, you can get the response from wavelengths which are more energetic than the color of the phosphor, which is inside the lead. So yeah, the nice thing about the red LEDs is that they, some of them at 100 microamps are around about the 1.65 volts of the P2's sensitive region. So you can kind of zoom in on the signals.
Well, I do believe you'd be far better off using them in a current mode, and the same thing when you get around to using the LM334, which will operate down to very low voltages. But if you do it without any pull-up resistor at all, I believe from the schematic and the mode of operation that Chip posted online a couple of weeks ago about the A to D converter, it's current balancing, right? So if you just allow that current to flow into the pin, it basically is ignoring that input resistor, and the A to D converter is balancing that current. And I'm still trying to get my head around that schematic diagram that Chip posted, but that's how I've used photodiodes and LEDs as photodiodes with the Prop 1 with the appropriate feedback resistor. It's just, instead of a resistor and a voltage providing that input current that needs to be balanced, the photodiode itself provides that current. And so long as it's held within range of, what the propeller, bounces back to it.
Yeah, we can go over that today later.
We can. I can dig out those results and show you what we found. We did a similar experiment and new to what we're doing with the temperature sensor, and happy to share that, but I'll probably also come back to it in coming weeks. The other thing with the P2, we've got a sort of a little Hello LED tutorial, which just shows you how to light up a LED 6 different ways. So not just blink a LED, but turn it on with different current or resistive biases. In order to use also the DAC mode to illuminate a LED. So just out of one pin, using different sort of configuration words, you can illuminate a LED many different ways, and I think that's a good way of getting across some of the I/O flexibility of the P2 smart pins.
Lachlan, quick question here. Seeking input from you and others as I see these examples get produced. I'm going to grab them. So they're not just scattered across the forums. And my current plan is just to make them downloadable files from the MicroPython Getting Started page on the P2 section of our website. So anyone that's looking for things should be able to go there and find them. I haven't put this one there yet, but if you have any other ideas of where I could store those examples or preference?
I don't really have a preference, and I think, a bit like the GitHub thing, I think we're probably going to need to put things in multiple places, as is the modern way. So, you probably find that you'll want to upload in the same information a few different ways, and, you might have one in video form, one in text form, and possibly in more than one location. So it sort of doesn't matter. Just the information, collating the information in the first place is kind of the initial challenge, and then where it gets stored, I think, is a lesser problem, and I think that'll probably evolve anyway over the coming years.
Well, great. Thanks for sharing this. I have a couple professors, a few of us are aware of, and then one big Python enthusiast in France who writes books who's all over this already.
Great. Okay, well, who wants to see a sparkler?
Light it up.
This will be, let's get the... It's hard to get underneath.
How come whenever males are working with electronics, fire is involved?
Fire good.
Ask Erco.
Oh yeah, Erco.
It's no fun.
This is one of those Australian sparklers.
It just won't.
There we go. Now we moved on.
There we go.
Right, now I've got to hit run. All right, we're getting near the sensor.
Oh, you mean
now.
it's having trouble because it's upside down?
Okay, there we go. So that's going past the sensor now.
Yeah. Leveled out. Nice.
Did it peg out?
What do we got? We got 16,000, whatever units they are. So that seems pretty reasonable. And I'll hit it with a bit of freeze spray. But I wonder if we.
Sensor.
It stopped running.
Oh yeah, the sensor just stopped running as we hit the freeze spray. So there you go. There's a sparkler, and now I'm going to try one more thing. And we've got a little camera here. I don't know if it'll work, but it's worth a try.
Are you going to find the burning point of skin so you can compare it to the sparkler?
No, I'm just looking.
I'm going to run an errand. Would you be okay for an hour?
Oh, yeah, this is going to go for an hour easy.
So what I'm hoping, this is a like a little thermal camera module, and what I'm hoping is that you can probably see the sparkler. It's pretty evenly hot actually all the way through. But there's, I don't know if you can see it, there's our LM335 with the hot sparkler behind it. I'll just click run on the new thing again.
Yep. That might have spun over somebody's head.
And here's some freeze spray. Pulling it down. So hopefully, I have no idea what you guys are seeing, but
purple blob.
Yeah, purple
we
blob
saw
is
it
cool.
go from bright yellow to purple.
Okay, and then if I warm up the sensor again with my fingers, you know, it's taking it back to 0. One thing you'll notice is that there's not a lot of noise on these. These waveforms are pretty clean, and that's a testimony to you know, Chip and Von Sarvis's design on that that evaluation board. You know, it's it does get nice, fairly noise-free kind of result when we hook up these sensors, and all we're doing is just twisting the wires. There's no screening or anything like that involved. So
Why does the program keep stopping? Is it just you have it timing out, or
yeah, what that window just does. It's got 100 elements, and so we literally just pump 100 values in. And you know, you can change that if you want it to go continuously. You just, you know, run it in a loop.
Lachlan, I have a stupid question.
Yeah.
Why did it go into minus degrees?
What it does in the code, can you see how it takes a baseline as the first reading?
Huh?
So that very first reading, that just becomes 0 in effect. And that's just so you don't get lost, because the actual normal baseline, if I just put this back on camera, is a value around 3 volts. And if you're using a million count in the ADC bucket, that means that value is somewhere up around maybe 750,000. It's just a big overwhelming value. So what we're actually doing is we're that sparkler that had a sort of a heat value of 16,000 count of the ADC of the million count range. That kind of value is riding on top of 750,000 or so. What I can probably do in MicroPython, if I just scroll up, can you guys still see the MicroPython screen?
I can.
Yep.
Yeah, I've got it.
When we run the experiment, if I just scroll up through the values, that very first, see the baseline value there?
Mm-hmm.
That's what, when you take an A to D reading of around 3 volts, this is what kind of value you get back when you've set it to sample over a million count, or a million clock ticks of the P2. And so 3 volts gets represented at about 783,000. So it's sort of most of the way towards its upper limit. It's sort of like, you know, it's getting towards its kind of upper limit. Chip designed the ADC so that they're up there. They can extend beyond the voltage rails. And so I think when you're at 3.3 volts, you might get a value of around 85,000, 850,000. And so, and when you're at 0 volts, you actually get a value of about 150,000. And that means the P2 can actually read a little bit above and below the rails, which is a feature, and it's by design. And it also gives you a nice kind of pulse density. You're not getting right down to absolute 0.
And you're doing a million counts. You're looking at it for a million clocks.
Yeah, I should say I can just change if that a million value is overwhelming. This thing should run fine with, like if I make that 1,000, just to make it easier to kind of, that should run just as easily. We'll just have to run it once to kind of clear out the values. And I think if you saw there, the baseline actually just clocked past at a value of 772. So it's just divided by 1,000. But this makes it maybe a bit easier for maybe school students to understand where the count is at. I'll just let it run through once, and then I'll click it a second time, and we'll actually.
Now you need to divide it by 100th of what you were dividing it before, right?
Yeah.
A thousandth actually.
Yeah. So now we're at we're down at 1,000 count, but of course you've got a bit more noise, like the signal to noise, because just from one bucket to another you might have one value different. You know, we're oscillating around 11 or 12. This is just with my fingers heating up the sensor. If I put the freeze spray on, you know, then it starts to look a bit more respectable. But yeah, the million count just gives you a finer granularity than you would otherwise have. So I think that's it for temperature sensors for this week. But we'll put multiple sensors on, and I'll upload onto that thread which is in general discussion on the P2 forum. So I'll put further examples which bring in the multiple sensors.